Welcome everybody. Today we are going to talk about essential limit theorem. And the big difference between what we were doing with the normal distribution, finding probabilities, and the essential limit theorem is that now we're talking about a population. Okay, we're talking about an actual sample size. So normally in our formula we only had sample mean minus population mean divided by standard deviation, which is really not realistic. We're going to be dealing with problems where we have a sample size. So our denominator, what that's going to be called from now on, is the standard error of the mean. Okay, our standard deviation is going to be affected by the square root of the sample size. Okay, we know that when we have a larger sample, that our standard deviation should become, our standard error should become smaller. Okay, and that's what this theorem is saying, is that if I do something 10 times versus 100 times versus 1,000 times, I should be reducing that error. So the larger the sample we have, the better off we are going to be as far as getting that error reduced, and the shape of the distribution will approach a normal distribution as that sample size increases. So this is the formula that we're going to be using from now on. So when we read a problem, what we want to identify is, what are the four pieces in this problem? So number one, it says AC Nielsen reports that children between the ages of 2 and 5 watch an average of 25 hours television per week. Assume the variable is normally distributed. Standard deviation is 3 hours. Okay, so that's always going to be the easy one. Standard deviation is 3 hours. 20 children between the ages 2 and 5 are randomly selected. Okay, so there's our sample size. Okay, we're selecting 20 people. Find the probability that the mean of the number of hours they watch television will be greater than 26.3, and again, that should be hours, not years, hours. There, little typo. Okay, so when we sampled 20 people, their mean was 26.3. That is the sample mean, compared to the population mean of 25 hours. So now we're going to draw our picture. Okay, the mean is 25. What's the probability that we're going to watch greater than 26.3 years? Okay, so again, the picture gives you an idea of what your probability is going to be. We know our probability is going to be less than 50%. Now we're going to use the formula. Sample mean minus population mean, standard deviation divided by the square root of the sample size. Okay, numerator is the easy part. For the denominator, we're going to take 3 divided by the square root of 20. Okay, and that comes out to be 0.671. Okay, standard error, we're going to go 3 decimal places just to be accurate. So 1.3 divided by 0.671. Remember, z-score is always 2 decimal places to look it up in the chart. So we're going to round that to 1.94. Okay, so just like we've been doing, once we know our z-score, we're going to look that value up in our table. 1.94. Okay, that z-score, the area to the left, is 0.9738. That would be the probability that they would watch less than 26.3 hours. So again, to find the probability that they would watch more, we're going to subtract, and that shaded area is going to be a very small probability, about a 6.2% chance. So again, identify your pieces, draw your picture, figure out what the z-score is, and then answer your question, what's the probability? All right, if we look at number 2, the average age of a vehicle registered in the U.S. is 8 years or 96 months. Okay, so the mean is 96 months. Standard deviation is 16 months. We're going to sample 36 cars. Okay, sample size is 36. Find the probability that the age of the cars is between 90 months and 100 months. So this is one of those questions where we're finding the probability between two items. The mean is 96. The probability we're going to be between 90 and 100 is what we're trying to figure out. Okay, so again, we have to find two z-scores. Z equals 96, Z equals 90 minus 96 divided by the standard deviation over the square root of the sample size. And we're going to use this same exact formula, except instead of 90, we're going to use 100 minus 96. So when you're doing something like this, when you do 16, I know the square root of 36 is 6, so I'm just going to do 16 divided by 6. The denominator is going to be 2.67, so write it for both. Save yourself the time. Difference there is 4, difference there is negative 6. So negative 6 divided by 2.67 is going to be a negative 2.25. And 4 divided by 2.67 is going to be a positive 1.5. Okay, so negative 2.25 falls here, positive 1.50 falls there. Okay, those were the two z-scores that we figured out. So again, a score of 100 is 1.5 standard deviations above the mean. Okay, and again, not a score, we're talking about months, the cars. 90 months is 2.25 standard deviations below the mean of 96. So go to your handy dandy chart. 1.5 is an area of 0.9332. Again, that's the area to the left. Negative 2.25 on the other side, negative 2.25 is going to be 0.0122. So again, to find the probability of these two, I'm going to subtract that small one away from the 9332. And when we do that, we're going to end up with a very large percentage. There's a 92.1% chance that your car is going to fall between 90 months and 100 months based on this distribution. Okay? So sample size is having an effect on our probabilities now, which is what the central limit theorem is saying. Okay, the more times we do something, the better off we should get as far as that error goes. We should get a more realistic approach to that normal distribution. Okay, so on this paper, I'm going to let you try 3 and 4. Okay.